So today I'm going to tell you about a toy problem that I've been working with lately that I think has some really interesting properties around disambiguating concepts of memorization and generalization within AI models. So for a starter question, how many of you are familiar with the concept of grokking? Please raise your hand. Sounds good, about like 30% maybe. This is a interpretability concept centered around the problem of modular arithmetic. It was first discovered in around 2021 by some OpenAI researchers. It's pretty simple. I'm going to walk you through it and then walk you through some of the modifications I've made to the standard setup to tease out some of these threads around memorization and generalization. So to start, we're dealing with the problem of modular arithmetic, which is pretty simple. It's just taking two numbers, adding them together, and taking the remainder modulo a certain value. So you can tell that with mod 97, we are just doing addition up until the result is greater than 97, at which point it wraps around and we go back to 0. Pretty simple. You can tell how there might be a natural cycle to this, how it might be natural to represent this toy problem with ideas around circles or spectra, that sort of thing. So for the sake of visualization, let's assign colors to this such that it also wraps around. You can tell we're starting with orange, wrapping around to orange-red, something like that. This naturally decomposes into a color spectrum, and that further decomposes into a circle, which conveniently is a pretty nice way to represent modular addition. This is because it has the interesting property that once you do this, you can start representing modular addition as rotations on this circle. So something like 3 plus 5 is a small rotation. A larger rotation that wraps around mod 97, like 50 plus 80, mod 97 is 33, wraps around the circle. So this is a general way to think about the problem of modular addition, which is what grokking uses under the hood. So what is grokking? Grokking is we take there's around 9,400 possible answers in a mod 97 modular addition problem. We take 30% of it, train the model on that 30%, and see if it generalizes to the other 70%. What happens is right away it memorizes the train set rather. It goes to 100% train accuracy, but for a long time it doesn't learn anything about the test set. And this is because it hasn't learned the rule that underlies all of modular addition. However, after you train it for a long time, what the OpenAI team found in 2021 is that something really interesting happens. All of a sudden, your test accuracy shoots up to 100% along with train accuracy because the model learns the rule that underlies all of the data. This is grokking. So what might be going on under the hood here? To find out, we can do this thing called the discrete Fourier transform, which represents the embeddings that the model has under the hood on a 2D spectrum that represents the sort of like cyclical energy that it has. So what happens is that at the very beginning, epoch 0, the embeddings cluster pretty randomly. You can tell that the model hasn't really learned any sort of meaningful structure. And as we keep going, we are increasing in test accuracy. And the model is getting sort of a circular representation where it's discovered that circles are a really natural way to represent the problem of modular addition. And by the time we get to the final state, it's learned this perfect structure where it's learned the ground truth, like trigonometric relationship between modular addition and the circle trigonometry representations. This is an interesting problem because it reduces the entire suite of 9,400 really complex facts into one simple rule that generates all of the data. The reason it does this is because we have two capabilities for representing the data. One is you can memorize all of the answers, and two is you can learn the rule that underlies all of the data. Memorizing is pretty easy because you just have to learn the specific examples. It tells you what it is right away. You don't have to have any sort of structure underlying your representations in order to do it. Generalizing has to be more structured, but the weights are smaller. And the reason that it selects generalization over memorization in the long run is because we're using this thing called weight decay in our model, which penalizes large weights and forces it to eventually go towards the more compact weight solution. So this is a cool problem, but it's a little bit straightforward because the test set and train set kind of optimally point to the correct answer because they're all weighted equally. It's almost like saying, hey, here's like a really obvious like structure that you should discover under the hood. It's kind of screaming at the model the whole way. So real world data sets aren't actually like this because there's a lot of noise and a lot of long tails in the data, not necessarily representative of the truth all the time. There's this thing called Zipf's law in language, and a lot of other phenomena behave this, such as like user behavior, which governs like a lot of data sets that you might encounter in the real world. So one obvious way of modifying the modular addition problem is to weight the examples according to Zipf's law, which makes a lot of the weights a lot smaller and upweights the loss that we're giving to a few examples. So this has the property that as we start to upweight the top examples more and more, the model starts to see fewer and fewer examples. So we're increasing the memorization pressure significantly, which arguably makes it more faithful to what real-world AI problems are like because the data they're being trained on has a lot of Zipfian characteristics in it. By the time we get to a Zipf exponent of 1.5, which just determines how heavy-tailed the data is, over 50% of the gradient actually comes from just 2 examples. So there's a really strong memorization pressure that you can dial up as much or as little as you like. And that's what I think makes this a really interesting problem. So what happens as we start dialing up the Zipf exponent and making the data more heavy-tailed? This is regular right here. The Zipf exponent is 0, but as we start cranking it up, we start to see oscillations in the test accuracy of the model such that it starts learning the correct solution and then forgetting it periodically. And as we crank up the Zipf exponent more and more, it actually becomes more and more severe oscillations till the point where it starts not being able to learn anything at all because the memorization pressure is so strong. This is an interesting thing that I think I haven't seen very often in machine learning, so my interest was piqued when I saw this. So one obvious thing that you might want to ask is, what is the model doing under the hood that causes this? So we're going to do the same projection onto a 2D axis that represents Fourier energy. And I've added a noise axis on the side here that represents sort of non-Fourier energy that doesn't correspond to this circular representation. So what you can tell with the Zipfian data is that it still learns the correct circle. And it actually learns it almost perfectly. It goes up to 100% and the noise goes down. But then as we keep going, it starts to destabilize the Fourier representations, and eventually the noise goes up, catastrophically interfering with the model's ability to produce the correct answers. Test accuracy drops, and then it recovers again. So why should this be the case? We have to look at the 2 forces that are acting on the model here in terms of where the gradients are pointing. One points towards the correct answer, which is generalization, and one points toward memorization. The force pointing towards weight decay, pointing towards the correct answer is weight decay, as discussed earlier, and the force pointing towards memorization is this Zipfian gradient that we've discovered. Far away, weight decay is much bigger than the Zipfian gradient, but as we get closer and closer to the correct representations, the weight decay starts going down in comparative magnitude because the weights become smaller because they've learned the small weights correct solution. At this point, the biggest force operating on the model is this Zipfian gradient that points towards memorization. And we get this collapse. But then the weights are big again, so weight decay can enforce its will again, so on and so forth. We have this cyclical behavior. It's called a saddle point in machine learning, stable when you're far away, unstable when you get there. So I think this is an example of the phenomenon of entangled memorization and generalization, which real-world LLMs really probably suffer from to quite a significant degree. In this particular problem and in real-world LLMs and other models, we have different types of abstractions that would like to compete for the same representational capacity. One that points towards memorization, one that points towards generalization, as discussed. The problem is that the deep representations that represent the data underlying process perfectly require structure to maintain, and it's pretty difficult to find them. So for an example of the entangledness of memorization and generalization in real-world models, here's an example from GPT-3. It turns out that the ability of GPT-3 to do arithmetic was heavily dependent, in some cases, on the particular context that you provided it. So in one context, asking about pencils, pens, and erasers, it couldn't do addition. In another, asking about animals, it could do addition. Why is the case? We don't really know, but this probably is an example of the entanglement of the generalization circuits with memorization circuits that activate in particular scenarios, such as, in this case, weirdly, animals. So I think this is an interesting toy problem going forward because it allows you to test out new methods of eliciting generalization with new types of approaches. You can try and solve Zipfian grokking with RL. You can try and do it with distillation. You can try all sorts of funky architectural solutions. And these various solutions may or may not point towards generalization. This gives you a pretty cheap way of finding out. And I have been using it to great effect. The code is all open source. A couple of people have cloned it already and have implemented their own versions, their own solution. So hope this was interesting, and hope you connect and clone the repo. Thanks very much.